We are going to introduce a paper in CNDR 20 workshop WANC, RNN-based approach to TCP throughput prediction. As we know, TCP is one of the most widely used transport layer communication protocols on the network. TCP uses many approaches to achieve high performances and avoid congestion collapse, where network performances can fail by several orders of magnitude. TCP congestion control protocol commonly used on device has been worked for about 30 years. Several current TCP congestion control schemas are used in the network, such as New Reno and Cubic. With the changes in network technology and network applications, such as bandwidth increasing, stream application, cloud games, and complex IoT device environment, current congestion control protocols are gradually no longer suitable for today's environment. The problem we faced is it's difficult for congestion control protocols to achieve idle throughput. There still are some space in the throughput of the current congestion control protocol for improvement. So let's see how Cubic works in the network. It's a picture to describe a cubic Windows growth function. Because it's a cubic function, it has two stages for Windows increasing. The first part, Windows max, is a concave function that quickly increases the Windows size when the last congestion event occurred. The second part, max probing, is a convex function. The cubic probe seeks a large bandwidth at a slower speed. Cubic spends a lot of time in two stages to stabilize the network. At the meantime, actually we could get a higher congestion window. In the picture, congestion window of green part could be improved. The rise of machine learning in recent years has brought new opportunities and challenges to congestion control, such as deep learning and reinforcement learning. With the help of machine learning, congestion control protocols can achieve higher throughput than current protocols. Our research goal is to improve TCP throughput by using recurrent neural network prediction. Applying machine learning to congestion control is meaningful to the development of the protocol. Even though we can't achieve ideal throughput, we can use some ways to get closer than the current congestion control schema. As we know, congestion window is changed with time. If we consider congestion window as a mass function of time, we will get a time series state. Also, recurrent neural network with echo states is suitable for reproducing certain time series. That's why we consider using recurrent neural network in this research. Let's introduce our approach. The first step is to introduce how recurrent neural network work in congestion control schema. The TCP client sends and receives state while obtaining the matrix in the network. The TCP client also inputs the matrix to the recurrent neural network, and the network will change the congestion window, thereby affecting the throughput. So, how do we change the congestion window to affect the throughput? We change the congestion window determined by the output of machine learning. We train to make the output value of recurrent neural network as a prediction, which we called P in the paper. Recurrent neural network will receive network matrix and make a prediction. Approach determines congestion window by the value of prediction. You may notice that the value of prediction is between 0 and 1. It refers to how we train the recurrent neural network models. Point 1 means the packet lost there. After the packet lost, in the first max probing, if congestion window of the next packet lost, I mean the point 2 is higher than the point 1, we set the prediction of the point 1 is inquiry 1, which we marked in green color in the picture. If the point 2 is lower than the point 1, we set the prediction of point 1 in query 0, which we use the red color to mark in the picture. Here is a picture to describe how we train recurrent neural network from congested data. In the picture, P is prediction of last congested window. Recurrent neural network includes some simple networks and some complex networks. It's important to select the most suitable type of recurrent neural network model. Also, the matrix used as input data for recurrent neural network model and the training should be selected such as they will significantly influence on the network's throughput. We prepared 8 groups of matrix for training and applied 3 types of recurrent neural networks in our approach design. Let's introduce all 3 recurrent neural network models. The first one is simple RNN. Simple RNN includes an input node, output node, and a memory control function. Those are LSTM unit and GRU unit. LSTM unit has a better control of gradient descent than simple recurrent neural network. It includes an input gate, output gate, and a memory gate. GRU is a little simpler than the LSTM model, but it also has a good control of gradient descent, and it has one control gate less than LSTM. Here is a list of all features we considered, of which we focus on the following features: TDUP-int and RTO-int. Those 2 features as input of recurrent neural network have a significant impact on the throughput prediction in the experiment. According to those important features, we set the experiment into the following 8 groups. Those 8 groups are based on 2 common network matrix groups, like Group 1 and Group 5. We test different important matrices in those 2 common groups. Let's introduce our test environment. We deployed the recurrent neural network algorithm and cubic on sender 0, and the cross traffic on sender 1, where the cross traffic is TCP or UDP, and all network links in the picture are 10 GB per second. We also instruct sender 0 to send 5 GB of data, which was randomly generated by Network Simulation 3, constant bit rate application. Our recurrent neural network models were designed based on the Keras and TensorFlow. And there are some default settings in the network we need to notice. Here is the throughput result of our experiment. Cross traffic of left throughput result is TCP. Cross traffic of right result is UDP. We achieved a 35% throughput improvement relative to the cubic model type in the first 8 seconds on a range which cross traffic is TCP. The approach also performs better than cubic when the cross traffic is UDP flow. Our approach is trained to predict the current value of congested window, so it can reduce packet loss rate. Also, it means some of our throughput improvement comes from low packet loss rate. We can see in both pictures, our approach has a lower packet loss rate than cubic. Conclusion: we developed a recurrent neural network-based TCP prediction approach, employed different recurrent neural network models, and investigated the impact of different network matrix groups. Our results revealed a throughput which is approximately 35% higher than the throughput achieved by cubic. It can be realized by employing our proposed prediction approach with an appropriate matrix group. Also, our recurrent neural network-based prediction models has considerable potential. It can be improved, Toward this goal, we plan to evaluate the fairness among multiple TCP connections in the future. Thank you for watching this video.